Hi everybody, and welcome back to another episode of Cellular and Wireless Unmasked. Today's topic is small cells, and we're going to talk about three things today when it comes to small cells. Why they're important to today's wireless networks, how they are different and how they are similar to oDAS nodes, and why they are so important to 5G, the fifth generation of wireless technology. But before we jump into that, I want to give a shout out to our sponsor today, Pacific DAS here in Pleasanton. And here's a little bit about Pacific DAS. Pacific DAS is a telecommunications firm located in Pleasanton, California. And Pacific DAS specializes in the design, engineering, and installation of both public safety DAS and cellular enhancement systems. Pacific DAS is IBWave and FCC certified, and Pacific DAS does their own installations, grid testings, and system certifications. For more information, reach out to Pacific DAS at www.pacificdas.com. Thank you. Okay, so let's do a quick review of oDAS. We spoke about DAS in a previous video, and oDAS, Outdoor Distributed Antenna Systems, were very popular in the mid to late 2000s as a way for the wireless operators to build a more efficient network for difficult to cover places like a canyon road or a country road where it would take multiple macros and cost considerable expense. DAS is not cheap, but it's cheaper than building multiple macro sites when you can build one macro site and then spread that coverage right where you want it via an oDAS network. Most of your oDAS nodes are very similar in nature. They're built on a pole, either metal, wood, or concrete. There are some composite poles now, but really this is a very, very common architecture. You'll have your radio or radios in the middle of the pole. At the top you'll have an antenna, or they'll be right near the top, either panels or an omni antenna. There's a couple of things that oDAS nodes need. They need a power source and they need fiber. That's very typical. Most of your oDAS networks are joined back to the central unit, the hub or the head end, by a fiber optic link. So that's your oDAS refresher. Now, when we get to small cells, we'll talk about how they came to be and why oDAS is so important. So oDAS. oDAS was primarily a coverage enterprise to get coverage in those specific areas that were difficult to cover. And one of the ways they did that is they took macro BTS equipment, the big cabinets of radios and filters and controllers that you had at your macro sites, to feed these DAS nodes. They also did something called simulcasting, where they would take one sector or one cell of a macro site and they would feed up to 8 oDAS nodes for maximum efficiency. They want to get the most bang for their buck, cover the most nodes with just one sector. So they would do simulcasting, and again, that's for coverage. That's to really extend where that one site can reach. In that time, the systems were fed with a giant piece of equipment, very big, very bulky, required a lot of power, a lot of cooling, and a lot of real estate to house. That was how oDAS started. But one of the things that happened in the evolution of cellular networks, the radio equipment that feeds macro sites got smaller and smaller and smaller until you had these relatively compact radio heads to feed antennas. So that kind of gave the carriers an idea. We've got these DAS networks, right? And they cover areas, and we're bringing on some new technologies. And this was really driven by the rollout of 4G LTE. When that came out, the carriers, most of the carriers had DAS networks in various places, and they want to get these new radios out. And they thought, well, we could put them in the head end in the hub, we could feed DAS nodes, or why don't we just take that radio and place it right on the pole? Put your small cell radio right there on the pole with your DAS remote, which is basically a repeater of your existing wireless infrastructure. This gave us kind of a hybrid model. And the reason the rollout started that way is you already had a permitted pole here. You already had infrastructure that was cleared by this jurisdiction. You already had your power. You already had your fiber. Small cell radios require power and fiber in most cases. So this all worked out really well. So the first generation of small cell nodes were hybrid nodes co-located with DAS nodes, and they look like this. So let's talk about the differences between an oDAS network and a small cell network. And there's one really important key differentiator I want you to be aware of. In a DAS network, you have a hub or a head-end, and that's where you have your BTS gear, and that's where you have your DAS head-end gear. The BTS gear, the radio heads, what they do is they feed the DAS converts that RF signal into light, and that light travels on a fiber optic link out to your DAS repeaters. All the DAS repeaters do is take that signal via fiber, convert it back into RF so it can link to mobile devices. That's what a DAS radio does. It's just a fiber repeater. So the key thing I want you to remember about a DAS network is the radios, and there can be a lot of them co-located with the DAS gear and the hub or the head end, are inside this central point, okay? That is an oDAS network. The nodes are very similar if you look at them as far as fiber and power and antennas, but there's a key differentiator I want you to be aware of. Now, if we're going to draw a small cell network, a lot of the same infrastructure is going to be in play, the power, the fiber. Your hub or your head end will have what's called a baseband unit. It's an aggregator of all the fiber signals coming in from each of the small cells. Now, here's where the big differentiator comes into play. Instead of your nodes just being repeaters, they're actually radios. So in a small cell network, you've got a giant small cell network, you still have a hub or a head end, but instead of having a DAS head end and radios, you've got a baseband unit, and that baseband unit is an aggregator that connects directly to an MSC, a mobile switching center, or an MSO, mobile switching office, for each of the wireless carriers. Verizon has a number, T-Mobile has a bunch, AT&T has some. That's their core network. So this baseband device takes all the small cells via fiber links and then aggregates that signal and gets it into the MSC. Now those radios are no longer in the hub or the head end. The radios are actually out at the pole. So in a DAS environment, your radios are co-located with the DAS head end and the hub, but in a small cell, they're out at the poles. So that's the big differentiator. The radios are hanging on the poles and they're close to the users. So instead of this device here being a fiber optic controlled repeater, it's an actual radio that generates your 1900, 2100, 700, 22.5 gig, whatever signal they're trying to replicate. Still have an antenna, they still look very similar, but the radio gear is out on the pole where the users are, where the mobile devices are. And I want you to understand that key differentiator between oDAS and small cells. So some of the pros and cons with small cells, they are very, very efficient for one operator. So when you have your pole, you typically place a couple of radios, 2, maybe 3 radios, but they're for one carrier. Your antenna's on the top somewhere, and you've got your radio somewhere around mid-pole. Each radio will transmit one frequency band, 1900, 2100, 700, 850. They just do one frequency band for one operator. So it's just that frequency band for T-Mobile, just that frequency band for AT&T, or just that frequency band for Verizon. Each radio is operator specific. So for one operator, for one of your wireless carriers, it's very efficient. They like that. They get all their radios onto one pole, and that kind of locks the pole down as their pole. Because one of the cons for multiple operators, the gear gets pretty big, pretty bulky. You need more power, you need more fiber. If you want to have more than one operator on a pole, each operator needs their own set of radios. So if you have 2 operators on a pole and they each have 3 frequency bands, you've got 6 radios. Poles can only handle so much weight. They've got loading limits. You can only have so many boxes hanging on a pole per jurisdictional requirements. So to take a small cell and make it multi-carrier, it's difficult. Now sometimes what they'll do, integrators and designers, they'll place a cabinet, a very small cabinet at the base of the pole, and they can put multiple radios in there and then feed the antennas with a coaxial system. That's a way to get multiple carriers, multiple frequency bands onto a pole. But the wireless carriers really love small cells because it allows them to get multiple signals down to where the people are offload that macro, and really give them pinpoint efficiency and a good signal for your devices. Now let's look at some of the small cell radios and how they're on the poles and how you can identify a small cell, and we'll tie that into how it's important for 5G. So let's talk about why 5G, fifth generation of wireless technologies, and small cells are so important. And they work together in a very specific way, and they're kind of dependent upon each other. When the wireless operators launched fifth generation wireless signals, they put their radios on their big macro sites. It gave them the best bang for the buck, it covers the most area, and that was all your sub 6 gig stuff. So not the most impressive. It is new technology, it is new radios, 5G NR, but the first step, the lower 6 gig, isn't the super impressive 5G. What is impressive is the 5G millimeter wave. That gives you your low latency, huge bandwidth, both uplink and downlink. You'll see downlink speeds 1 gig, 2 gig, up to 3 gig off these millimeter wave sites. They're in the 20, 30, almost 40 gig bandwidth, so they're really, really high frequency. Now, how that ties into small cells, if you put millimeter wave on a giant macro site, 200-300 foot tower, the 5G millimeter wave propagation is very short. It doesn't go very far. It doesn't travel like the lower bands do, the 700, 800, even the 1900. Very high frequencies tend not to propagate too far. The lower frequencies go a lot farther. So if you put millimeter wave on this big tall site, you're going to create a really nice bubble of coverage high up where there aren't many users, if at all. And the users who can see it won't have a great experience. It won't be much better than 4G if they can see the signal at all. That's just due to the physical properties of how millimeter wave, those high frequencies, propagate. So what they did is, they've already got 4G on small cells, on poles. So what they did is that they took the 5G active antenna radios, put them on the small cell, and what that does is, that brings that millimeter wave down to where your device can connect to it with a nice robust connection. And that gives you those super impressive speeds. So this bubble of 5G millimeter wave, if you're down here on the street, you can't really connect to that with your mobile device. But that same size bubble on this small cell down here, you're gonna connect to that. You're gonna see that device. You're gonna see this 5G radio, and you're going to have that very impressive low latency, high bandwidth experience on your mobile device. So what I want to do now is show you a couple of examples of standalone 5G and 5G with 4G. In short, if you see a standalone site, a pole with a couple of boxes, usually 2 or 3, remember the 5G radios are active radio antennas. You can't really separate the radio from the antenna due to the loss in the cables. The cable loss is so high at millimeter wave, it doesn't make sense to separate the radio from the antenna. So they're typically one device, an active antenna. So you'll see a box by itself near the top of the pole, and it looks like this. So you've got that 5G radio at the top, you know how to see it. It's just a very, very simple plain box. Some jurisdictions will put a hexagonal shroud, kind of a concealer at the top to help it blend in a little bit better than just seeing a radio sitting there by itself. But they do have the 4G, 5G combo sites. Those are very common in a lot of jurisdictions. And you'll have your 4G radios on the side of the pole. You'll have your 4G antenna at top, and you'll have your 5G radios right below the 4G. And that's what we call kind of a combo hybrid 4G, 5G site. All the radios still need power and fiber, just like an oDAS, just like a standalone small cell. So you've got a lot of fiber going into these poles, and you've got a lot of power going into these poles. They look like this. So one of the key drawbacks to oDAS networks and small cells is they're very expensive. So the infrastructure required to get to a pole and create a small cell or DAS network requires fiber and power. We talked about that already. It can be very, very difficult to get fiber circuits to a pole. A lot of undergrounding has to take place in your metropolitan areas, even the aerial fiber on wood poles. Most jurisdictions are very strict, and they have a lot of regulations about where the fiber needs to go, what kind of clearances you have to maintain from other comms, and they're really picky about the distance required from any kind of power, either primary or secondary. So there's a lot of regulations that go into deploying the fiber. The power can be close to the pole, it can be on the pole, but in some cases it's not. Sometimes a jurisdiction will let you share power with their street light, sometimes they won't. It all depends upon how much power they have available. So when you look at what it takes to build a small cell node, it gets really pricey. Sometimes the pole has to be replaced to support the antenna and the radio gear. That's a big cost. Sometimes the foundation has to be dug out and re-poured, and you have to put a rebar cage in. So all these factors, the fiber, the power, the physical infrastructure, makes small cells very expensive to deploy. And that goes for 5G as well. So the 5G millimeter wave is such an impressive technology, but it's so critical to small cells. The only way that 5G millimeter wave is going to exist out in the public space is through a network of small cells, and they're very expensive. So the carriers were really running around in the last couple of years deploying small cells, putting 5G radios out there. It's kind of curtailed a little bit. They're still building them, and they're still evaluating the expense and where they're going to put their money to get the best ROI using small cells to bring you 5G. So really, that's small cells in kind of a nutshell, how they came to be, how they operate. Again, very similar to oDAS, but it's where that call processing takes place. It's out there at the pole. The radios have left the shelter. They've left the macro. They're on the pole today. So we're seeing a big rollout of small cells, especially those in their areas that already have fiber and power, and it's easy. They go ahead and they deploy them. But if you have any questions about today's topic, please put it in the comments below, and I'll do my best to answer it for you right away. And again, I thank you so much for your time and your attention today. I always love it when you like and subscribe to my videos. I'll get some more rolling here in the near future. Thanks again for watching Cellular and Wireless Unmasked. My name is Martin Hevesy. It's a pleasure to bring you some information today. Thank you.